In Chapter 6, we turn to thermodynamics and kinetics of chemical reactions, and then we'll quickly move on to mechanisms in this chapter as well. So in organic chemistry, we really focus on looking at functional group transformations when we look at chemical reactions. We look at stereochemistry and also where in the reaction or where in a molecule a reaction occurs. That's called regiochemistry. We also look at energy, and we definitely look at the mechanism or how the reaction occurs, or how bonds break and in what order. So let's start here with thermodynamics, and we use thermodynamics to talk about the position of equilibrium. So in other words, how much product we expect to get, if any. And so thermodynamics, you can see, describes how energies change over the course of a chemical reaction, and then what the amounts are that we can expect at equilibrium of products and reactants. So shown here is an exothermic reaction, and you can see that the top part is, and this is an energy diagram. So the reaction is going forward, and energy is increasing over here on the vertical axis. You can see the bottom part, the difference in energy between the reactants and the products. That's what we're talking about when we talk about thermodynamics. We'll look at kinetics in the next video. So these, like I said, these are energy diagrams, and the reaction on the previous page and then this one on the left, the products are lower in energy than the starting materials, and that's favorable. Things want to move toward lower energy, and they release energy when they do that, and we call that an exothermic reaction. That energy can actually be harnessed and used for other things in some cases. So then we also have endothermic reactions. In these reactions, we have to put energy into the system to make the reaction happen, and the product is then higher in energy than the starting material. So there are two key thermodynamic relationships to remember that can help us think about the relationship between delta H and delta S, entropy and work, or Gibbs free energy, and also the equilibrium constant. So let's look at this first equation first. And the overall idea of this tells us that equilibrium favors the species lower in energy. And so if you have a delta G that is overall for your reaction that is greater than 0, then your equilibrium constant will be less than 1, meaning that you're not going to get a whole lot of product, you'll mostly have reactant. On the other hand, if your delta G is negative, then you're going to have an equilibrium constant greater than 1, meaning that you get more stable products and you get more products. So notice the relationship here, that whatever is most stable is the thing that you're going to have the most of at equilibrium. So you could kind of plug these numbers in if you wanted to, but just to give you some representative values here. You can hear my kids yelling in the background there. When delta G is actually 0, that means that there's no energy change from the reactant to the product. Your equilibrium constant is 1, and that means that you have the same amount of A and B. So if you have that positive delta G, then you start to get an equilibrium constant that favors the reactants. And then if you have that negative delta G, it favors the products. So now let's look briefly at the Gibbs free energy equation, and this will lead to helping us estimate the energy of the reaction and therefore estimate whether we think a reaction will go forward or not. And so delta G is equal to the change in enthalpy minus the temperature times the change in energy, or change in entropy. And So the thing to realize about this equation is it's really just telling us that in order for a reaction to occur spontaneously, entropy has to increase somewhere because entropy is times arrow. Entropy is the thing that we say that has to increase as time goes forward. And so in order for you to have a favorable delta G, in other words, it be less than negative, one way for that to happen is to have a negative delta H, in other words, for the reaction to be exothermic. And in that case, when your reaction is exothermic, your entropy is actually increasing in the environment because more heat is released, or heat is being released that heats things up. They move around a lot more, and so you're increasing entropy. So one way for the reaction to be spontaneous is for entropy to increase in the environment. It can also, or instead, increase in the system itself. And in that case, you might have one reactant that is reacting to give you two products, or something else within the reaction where you're getting an increase in entropy in the reaction itself. So one way or the other, you have to have it increase in entropy in order to have a spontaneous process. It's just how the universe works. So in organic chemistry, within the system, like within our reaction, we often don't get a big change in entropy. And that allows us to kind of say that this term right here of this equation is approximately 0, and delta G is approximately equal to the change in enthalpy. And delta S is around 0 for a lot of organic reactions because you're starting with one thing and you wind up with one thing, and so you're not really changing entropy appreciably. So we're just going to go ahead and use enthalpy kind of synonymously with our Gibbs free energy. And in order to estimate enthalpy, we can use bond energies. And so whenever we break a bond, we have to put energy into the system. That's going to be a positive number. Whenever a bond is formed, energy is released. We get something that's lower in energy. It's exothermic. And the enthalpy is going to be negative. By conservation of energy, these are going to be equal and opposite values. So you can use these bond dissociation energies to calculate enthalpy change. And what you do is you take the sum of all of the bonds that are broken and then the negative of all of the bonds that are formed, because remember, we have to put energy into the system to break bonds, and we get energy out to make them. So these values are negative, these are positive. And then you just add those all up and you get the overall enthalpy change. And so there's tables. You'll see tables like this on your tests, and there's one in your textbook. And there's some, like, notice that tertiary carbons might have slightly different numbers than secondary carbons, which are different than primary and then methyl carbons. And so you do get some differences in enthalpies based on primary, secondary, tertiary. You can see some of those over here. Here there's a double bond with a carbon, or a triple bond with a carbon bonded to a hydrogen, and that's going to be different than a double bond bonded to a hydrogen. And so there are some differences that you can see even when you're talking about like a CH bond. But this doesn't dial in super specifically to different functional groups. So it really is an estimate. And so here's an example of this. Here in this case we have an OH bond. It's actually a carbon-oxygen bond that's being broken, and a carbon-oxygen bond that's being formed. And since Since we don't really have a lot of details about what the difference is between a carbonyl bonded to an oxygen and then just a carbon and sp3 hybridized carbon bonded to an oxygen, we have to assume that those bond energies are about the same. And so those would be about 91. And so 91 plus 91 minus 91 is equal to 0. So we don't really see overall, so the change in enthalpy and the change in Gibbs free energy is about 0. And we've already said that if you have a delta G or delta, and we approximate that with delta H at 0, then your equilibrium constant is 1, which means that you have about half of your products and half of your products and half of your reactants at equilibrium. And that turns out actually to be the case for this reaction. It's a pretty good estimate. It's about 50-50 products and reactants at equilibrium. So bond dissociation, these are just a few caveats. In other words, bond dissociation energies are really a rough estimate, but they work out in a lot of cases. So they don't tell us anything about the reaction mechanism. They actually have been determined in the gas phase, which is, again, just an estimate for the liquid solvents that we're usually using. And they actually assume that the reaction is a radical reaction, not a polar reaction. But again, that difference kind of gets subtracted out. So lots of estimates, and it gives us roughly a good idea of whether the reaction will occur or not.